After learning the Earth and the solar system, today let's discuss about chapter 27, Stars and Universe. Hi guys, Dennis here. This video is brought to you by Ace with Dennis. Now, learning can be smart, not hard. Don't forget to subscribe and press the bell notification button to stop missing out free lessons from me. In this lesson, we are going to learn the Sun, which is the closest star to us, and many other stars in the universe, followed by the Milky Way, which is the galaxy that we are staying in, and many other galaxies in the universe. We also will learn the birth or the formation and the depth of the stars. Next, we'll learn the Doppler effect, which will bring to the red and blue shift. Then we also will learn the Big Bang theory and its evidences. Finally, we'll learn Hubble's law, which can tell us the age of the universe. So stay tuned in this lesson. Let's start the lesson by learning the closest star to us, which is the Sun. As we know, the Sun lies at the center of the solar system. It makes up more than 99% of the mass of the solar system. From the formula force of attraction between two masses, F equals G m1 m2 over r squared, the mass of the Sun is much greater than other planets. Hence, the gravitational pull force of the Sun keeps the planets orbiting the Sun. We know that the Sun is a very huge star comparing to the Earth, but it is actually medium-sized star compared to other stars in the universe. It consists of mainly hydrogen and helium, and it radiates infrared, visible light, and ultraviolets. If we look up at the sky, especially at night, this is what we will see. The sky is full of white dots. These white dots mainly are the stars which are very, very far away from us. There are billions of stars in the Milky Way, come in wide range of sizes and colors. They are classified based on their color. The colors they emit tell us their surface temperatures. Here is the range of the colors of the stars that we can observe from the sky. As you can see, it is made out of blue colors all the way to the red color. To us, blue color is a cold color, while the red color is the hot color. But do they tell us the temperature of the star? Here is how the actual surface temperature of these stars based on their colors. As you can see, blue stars actually are the hottest stars, while the red stars are the coldest stars. So, the surface temperature can range from 30,000 Kelvin or 29,727 degrees Celsius all the way to 3,000 Kelvin or 2,727 degrees Celsius. So, the surface temperature of the Sun is about 5,600 degrees Celsius. Where is the Sun? The Sun is within somewhere here. So that's the reason we can see that our Sun is about orange or yellow color. And if we compare to many other stars in the universe, it is actually not a very hot star. Nuclear fusion in stars. Nuclear fusion happens in the center of a stable star. The nuclear fusion reaction releases a huge amount of energy. This is the chemical equation of the nuclear fusion reaction. In the nuclear fusion reaction, hydrogen isotopes, deuterium, which has 1 neutron and 1 proton, and tritium, which has 2 neutron and 1 proton, are fused together to form helium under extremely high temperature and hence high pressure. The pressure prevents the star from collapsing under its gravity. Let's recap this question, which we have discussed in Chapter 25, Atoms and Radioactivity. The question is, why is it currently not possible for hydrogen fusion to happen on Earth? And here is the reason. Hydrogen nuclei carry positive charges. There is a repulsive force between two hydrogen nuclei. Extremely high temperatures are needed to provide the nuclei enough energy to overcome the repulsive force. And at the moment, we can't achieve these extremely high temperatures. Hence, it is currently not possible for hydrogen fusion to happen on Earth. Now, let's discuss the Milky Way. The Earth is one of the 8 planets in the solar system orbiting the Sun. The Sun is one of the billions of stars in a galaxy called Milky Way. Like the Sun, some of the stars have some planets orbiting them. The universe is made up of hundreds of billions of galaxies. Can you imagine how big is the Milky Way and how big is the universe? Let's take a look in the next slide. This is the Earth, the planet that we are staying on. And this is the solar system. The Earth is one of the planets in the solar system, which is located here. This is the Milky Way, and the solar system is somewhere in the Milky Way. As we know, Milky Way is a galaxy, and there are many other galaxies that form the universe. Now, can you locate where is the Earth? We are extremely tiny in the eye of the universe. Now, let's discuss astronomical distances. We know that the SI unit for length or distance is meter. For longer length, we usually use kilometers. For astronomical distances, example, distance between stars and galaxies, are too large and not practical to use meters or even kilometers to measure. The speed of light in space, which is 3 times 10 to the power 8 meters per second, is believed to be the fastest speed in the universe, and nothing can travel beyond that limit. Light year is used for astronomical distances. So how much is 1 light year? So 1 light year is the distance traveled by light through space or vacuum in 1 year. Now if you want to convert the distance of 1 light year to meters and kilometers, here is how we can calculate. First, we take the speed of light multiplied with the time travel in a year in seconds. So we know that the speed of light is 3 times 10 to the power 8 meters per second multiplied by 365 days a year and multiplied by 24 hours per day multiplied by 60 minutes per hour and multiplied by 60 seconds per minute. We'll get 9.4608 times 10 to the power 15 meters, or change to kilometers, it will be about 9.5 times 10 to the power 12 kilometers. The closest star from the Earth, which is Proxima Centauri, is 4.24 light years away from the Earth. The distance of the largest star, which is UV Scuti, from Earth is about 9,600 light years from the Earth. The diameter of Milky Way is about 105,700 light years. Andromeda is the nearest galaxy to Milky Way. It is 2.537 million light years far from the Milky Way. Next, let's learn star formation. All stars will go through 3 stages to become a star. The first stage is nebula. A nebula is a giant interstellar cloud of hydrogen gas and dust. All stars are formed from nebula. The second stage is protostar. The force of gravity within a nebula pulls the particles closer together until a hot ball of gas is formed. This hot ball of gas is called protostar. As the particles are pulled closer together, the density of the protostar increases. This causes more frequent collisions between the particles, hence the temperature increases. The third stage of star formation is the main sequence star. When the temperature of the protostar is high enough, nuclear fusion reactions will occur within its core. Hydrogen nuclei will fuse to form helium nuclei. The nuclear fusion reactions release heat and light energy which keeps the core hot. When a star initiates fusion, it is known as main sequence star. In this stage, the star is in equilibrium and stable, which means that the inward force due to gravity is equal to the outward pressure force from the fusion reactions. Once a protostar is formed, its life cycle depends on its mass. As we have discussed previously, all stars are formed with the first three stages. The first stage is the stellar nebula, followed by the second stage is the protostar, and the third stage is the main sequence stars. Once it becomes the main sequence star, then it will depend on its mass, and we can compare it to the Sun. If it is similar size with the Sun, this star is considered as low mass star. The next stage after main sequence star will be the red giant star, followed by the planetary nebula, and the next stage will be the white dwarf, and at the end it becomes black dwarf. If it is larger or much larger than the Sun, it is considered as high mass star. So the next stage after main sequence star will be the red supergiant star. Next, followed by the next stage is supernova, and next stage will be the neutron star, and at the end it becomes a black hole. So we'll discuss one by one after this. For the low mass stars, after it has gone through the first three stages of star formation, the next stage is the red giant star. So for red giant star, it happens after several billion years since it initiates fusion, which is from the main sequence star. Due to running out of hydrogen that causes the fusion reactions, the core starts to die down, shrink, and heat up. The core shrinks because the inward force due to gravity becomes greater than outward force due to the pressure of the expanding gases as the fusion dies down. New series of reactions will occur around the core. Example, helium nuclei will undergo fusion to form beryllium. The reactions causes the outer part of the star to expand. A star with a mass of 8 times the mass of the Sun or smaller will become a red giant star. Now the question, why does a red giant star red in color? This is because the outer surface of the star starts to cool down. After the red giant star, the next stage is planetary nebula. So what is a planetary nebula? The star becomes unstable and ejects the outer layer of dust and gas after finish the second stage of fusion reactions. The ejected layer of dust and gas is called a planetary nebula. After planetary nebula, the next stage is the white dwarf, and the last stage is the black dwarf. A white dwarf is due to the pull of gravity. The core of the star collapses completely at this stage. The white dwarf cools down and the amount of energy emitted decreases. And the last stage, the black dwarf. At this stage, the star has lost a significant amount of energy. Cooling process will continue until it eventually disappears. Next, let's talk about high-mass stars. After completed the first three stages of star formation, the next stage will be the red supergiant. What is a red supergiant star? The hydrogen causing the fusion reactions in a star starts to run out after several million years. A high-mass star, which is 8 times or more than the mass of the Sun, is called the red supergiant star at this stage. Fusion reactions in the core starts to die down. Series of shrinking and heating up periods happen in the core. Outer parts of the star will expand and contract. Fusion reactions will form elements all the way up to iron. Fusion reactions cannot continue once iron is formed. After red supergiant, the next stage is supernova. In supernova, when the fusion reactions cannot continue in the red supergiant, the core will collapse suddenly and cause a gigantic explosion. It is called a supernova at this stage. At the center of the explosion, a dense body will form. This dense body is called neutron star. During the explosion, the outer remnants of the star are ejected into the space, forming new clouds of dust and gas, which is called nebula. The nebula from a supernova may form new stars with orbiting planets. After supernova, the next stage will be neutron star and finally black hole. Neutron stars and black hole. For very massive stars, neutron star that is formed at the center will continue to collapse under the force of gravity until a black hole is formed. A black hole is extremely dense in a space where not even light can escape from it. Now, let us discuss the Doppler effect. Let's look at this animation. When a stationary object emits waves, the wave fronts spread out symmetrically. When the object moves, the waves it emits will stretch out and become squashed, as shown in the second diagram here. A moving object will cause the wavelength lambda and the frequency f of the waves to change. From the formula v equals to f lambda, f will be v over lambda, where v, which is the speed, is constant, which means the frequency is inversely proportional to the wavelength lambda. The wavelength of the waves in front of the source decreases. The frequency of the waves at this region increases. The wavelength behind the source increases. The frequency of the waves at this region increases. This effect is called the Doppler effect. Now we'll talk about the red and blue shifts. Let's recall electromagnetic spectrum, which we have learned in electromagnetic waves chapter. So the first wave is radio wave, followed by microwave, infrared, and visible light. For visible light, it consists of 7 colors. The first color is the red light, orange, yellow, green, blue, indigo, and violet. Outer visible light will be ultraviolet, X-ray, and gamma ray. So here is the red light and here is the blue light. As you can see from here, for the red light, it has larger wavelength lambda and smaller frequency f. For the blue light, it has smaller wavelength lambda and larger frequency f. So, why is it so important to know about the red light and blue light? The Doppler effect affects the color of light observed. Let's look at this diagram. If an object moves away from an observer, wavelength of light increases. Since the light moves towards the red end of the spectrum, this is known as redshift. Now the question is, what is redshift? It is an increase in the observed wavelength of electromagnetic radiation emitted from receding stars and galaxies. Now, let's look at this diagram. This is a stationary star relative to the observer. Lights in all directions have the same wavelength and frequency, so it doesn't matter where you want to observe this star. If it is relatively stationary to you, you'll see the same type of star in any direction. How about a moving star? So in this diagram, the star is moving to the right. If an observer observes the star in this position, he will see the light with large wavelength and low frequency. This is called the redshift. So light from a star that moves away an observer will be redshifted. If another observer observes this moving star in this position, he will see lights that has small wavelength and high frequency. This is called the blue shift. Light from a star that moves towards an observer will be blue shifted. Now, let's learn how to compare the light spectrums between the Sun and a distant galaxy. So this is a light spectrum with the red end and the blue end. Inside the light spectrums, we can see the black lines. So this is the light spectrum of the Sun, which is the nearest star from Earth. This is another light spectrum, which is redshifted. This is the light spectrum from a distant galaxy. And as you can see from the animation, it is redshifted. There are billions of galaxies in the universe. Milky Way is just one of the many galaxies. Light emitted from distant galaxies appears redshifted compared to the light emitted on Earth. The diagram shows that the light emitted from distant galaxies coming to us is redshifted. This is because the lines on the spectrum are shifted towards the red end. Now let's look at this diagram. This is a distant galaxy and this is the Earth. The light traveled from the distant galaxy to the Earth is redshifted, which can be shown on the light spectrum. So from this observation, we can make some points here. The first point is, this indicates that galaxies are moving away from the Earth. This is because the universe is expanding, and this observation supports the Big Bang theory. We'll talk about the Big Bang theory later. The second point that we can make is, the greater the distance to the galaxy, the greater the redshift. And also, the further away the galaxy from us, the faster it moves away from us. Using this information, we can plot the graph of the distance and the redshift. So from this graph, these few galaxies are closer to the Earth, and the light comes from these galaxies are less redshifted. These are the galaxies that are further away from the Earth, and the lights come from these galaxies are more redshifted. Now, let's discuss the Big Bang theory. The Big Bang theory explains how the universe started. Here is the Big Bang. About 13.8 billion years ago, the universe began from a very small region that was extremely hot and dense. A giant explosion, called the Big Bang, happened. The universe expands from a single point, cools down, and forms the universe today. Each point in the universe expands away from the other points. This can be observed from galaxies that move away from each other. The further away they are, the faster they move. As the result of the initial explosion, the universe continues to expand. This can be observed by the redshift in the light from distant galaxies, which is evidence that the universe continuously expanding and supports the Big Bang theory. There are four sources that support the Big Bang theory, which are the galactic redshift, cosmic microwave background radiation (CMBR), mixture of elements, and looking back time. In our lesson, we only talk about galactic redshift and CMBR. Galactic redshift as evidence for the Big Bang theory. So this is the light spectrum from the Sun as our reference because the Sun is the closest star from us. This is the light spectrum from a nearby galaxy, and this is the light spectrum from a distant galaxy. The spectral lines from the distant galaxy move closer to the red end of the spectrum. Here's the reason. Light waves are stretched by the expansion of the universe. Wavelength increases and frequency decreases. The light spectrums produced from distant galaxies are more redshifted than nearby galaxies. This shows that the greater the distance to the galaxy, the greater the redshift. The further away the galaxy, the faster it moves away from the Earth. The observations prove that the universe is expanding, hence support the Big Bang theory. Cosmic microwave background radiation (CMBR). So CMBR is the second evidence that supports the Big Bang theory. So here is an introduction to CMBR. So what is a CMBR? The CMBR is the afterglow radiation left over from the hot, dense state of the early universe, observable today as a faint microwave signal that fills the entire sky. It was discovered accidentally by Arno Penzias and Robert Wilson in 1965, who were awarded the Nobel Prize in Physics in 1978 for their work. Here are some characteristics of CMBR that make it a reliable evidence of the Big Bang theory. First is its uniformity. The CMBR is remarkably uniform in all directions, with only tiny fluctuations, which is anisotropies in temperature. Second characteristic is the temperature. The CMBR has a very uniform temperature of approximately 2.725 Kelvin. The next characteristic is the spectrum. The radiation has a black body spectrum, indicating it is the cool remnant of the hot, dense early universe. Here is how CMBR is connected to the Big Bang theory. First, it is an evidence of the hot early universe. The CMBR is a relic from a time when the universe was hot and dense. As the universe expanded, it cooled and the radiation stretched into the microwave region of the spectrum. The predictions are confirmed. The Big Bang theory predicted that the existence of this background radiation before it was discovered. The predicted and observed properties of the CMBR match, providing strong evidence of the Big Bang. And also the age of the universe. Analysis of the CMBR provides an estimate for the age of the universe which is approximately 13.8 billion years. Small temperature fluctuations. These tiny variations in temperature, which is about 1 part in 10,000, are due to the density fluctuations in the early universe. This is a CMB map which covers the observable universe. As you can see from the map, there are two regions here. The first region is the red or orange regions. They have warmer temperature and higher density of galaxies. The second region is the blue regions. In this region, they are cooler temperature and have lower density of galaxies. According to the Big Bang theory, the early universe was an extremely hot and dense environment. Hence, it must have emitted thermal radiation. Now, the radiation is in the microwave region. Over the past 13.8 billion years, the universe expanded and the radiation from the Big Bang has become redshifted. In the early stage, the radiation was high energy towards gamma end of spectrum. As the universe expanded, the wavelength of the radiation increased. Over time, it has increased so much till now it is in the microwave region of the spectrum. This is how the cosmic waveform looked like. At the beginning of the waveform, it is the waveform 300,000 years after the Big Bang. As you can see from here, this waveform has short wavelength. After redshift for over 13.8 billion years after the Big Bang, which is present, the wave has changed to larger wavelength. At the beginning, the temperature is also very high, and till present, the temperature is very low. The CMBR is very uniform and has exact profile expected to be emitted from a hot body that cools down over a very long period. So, what are the implications of the cosmic microwave background radiation? First is the confirmation of the expanding universe. The existence of CMBR supports the theory that the universe has been expanding from a hot, dense initial state. It also supports for the Big Bang nucleosynthesis. The CMBR also supports the predictions about the formation of the first elements, which is Big Bang nucleosynthesis, as the observed abundances match theoretical predictions based on the Big Bang model. The conclusion that we can make here is that the cosmic microwave background radiation, CMBR, is one of the strongest pieces of evidence supporting the Big Bang theory. Its uniformity, temperature, spectrum, and the detailed maps of its anisotropies align perfectly with the predictions made by the Big Bang theory, confirming the theory's validity and providing deep insights into the early stages and evolution of our universe. Now, let's talk about Hubble and the age of universe. So this is Hubble. His full name is Edwin Hubble, and he was an American astronomer who is known for his discovery that there are other galaxies in the universe beyond the Milky Way. By observing the absorption line spectra produced from the light of distant galaxies, Hubble discovered that the universe was expanding. So here are some light spectra from the lab reference all the way to the very distant galaxy. So here are some Hubble's observation and explanation. The first point is the light was shifted towards the red end of the spectrum. So this is the red end and this is the blue end. As the objects are getting further away, the lines will move towards the red ends. So the reason is because the Doppler shift in wavelength of light is evidence that the distant galaxies are moving away from the Earth. The second point is the more distant a galaxy from the Earth, the more red-shifted the light emitted the galaxy. This shows that galaxies or stars which are further away from the Earth are moving faster than the galaxies that are nearer. Hubble's law. Hubble's law states that the recessional velocity v of a galaxy is proportional to its distance from the Earth. So here's the formula based on the definition. V equals to HOD, where HO is the Hubble constant in the unit of per second, which is 2.3 times 10 to the power of negative 18 per second. V is the recessional velocity of an object, or the velocity of an object moving away from an observer. The unit is in kilometers per second. And d is the distance between the object and the Earth in kilometers. Now, let's learn how to calculate the age of the universe. From Hubble's law, we can modify the formula, which HO equals to V over D. Based on this equation, we can define the Hubble's constant HO, which is the ratio of the speed at which the galaxy is moving away from the Earth to its distance from the Earth. And if we reciprocal the equation, it becomes 1 over HO equals to D over V. Recall that the speed V is equals to distance D over the time T. And we can rearrange this equation to make T the subject. So T equals to D over V. Now, go back to the reciprocal of the Hubble's constant. It is also D over V. So this tells us the age of the universe. Now, to calculate the age of the universe, it will be just 1 over the Hubble constant, which is 2.3 times 10 to the power of negative 18. If we calculate the value, we'll get 4.348 times 10 to the power of 17 seconds. And now we can convert this into years. So by multiplying 1 minute per 60 seconds, multiply 1 hour per 60 minutes, multiply 1 day per 24 hours, multiply 1 year per 365 days. And we calculate everything, we will get 13.8 times 10 to the power of 9 years, or 13.8 billion years. If we plot the graph of the Hubble's law, V equals to HOD, this is what we will get. From this graph, we can see that the gradient is the Hubble's constant HO. The closer galaxies to the Earth move slower, and distant galaxies move away from the Earth at faster velocities. The key takeaways from the graph are: the furthest galaxies appear to move away at the fastest speed. The gradient of the graph can be used to determine the age of the universe. The point where distance equals 0 represents all the matter in the universe started at a single point. The unit of gradient is per second, or hertz. Reciprocal of the gradient gives us an estimate of the age of the universe. Now let's look at this example, which involves calculations using Hubble's law. The distance of the largest star, UY Scuti, from Earth is 9,600 light years from the Earth. Using Hubble's law, determine the velocity of the galaxy moving away from the Earth. Given that HO equals 2.2 times 10 to the power of negative 18 per second, 1 light year equals 9.5 times 10 to the power of 15 meters. Okay, do take note that in the previous example, I mentioned that the Hubble's constant is 2.3 times 10 to the power of negative 18 per second, But for this example, we use 2.2 times 10 to the power negative 18 per second. And usually this value is used in the exam. Alright, now here's the solution. So what we need to do is we need to calculate the distance given in light years. We have to convert it into meters. Alright, so now 9,600 light years we multiply with 9.5 times 10 to the power 15 meters because 1 light year is equals to this amount. Alright, when we calculate everything, we get 9.12 times 10 to the power 19 meters. Now we can apply the Hubble's law, V equals to HOD. HO given is 2.2 times 10 to the power negative 18. Then times with the distance 9.12 times 10 to the power 19. We calculate everything, we'll get 200.64 meters per second. Alright, that's all for this video. Thanks for watching. Do you have any questions or doubts to ask? Feel free to write it down in the comment area. I would love to hear from you. Do you like this video? If yes, please don't forget to like it and share it with your friends. Support me. If my videos benefit you in your learning, you can treat me a cup of coffee. To do this, link is at the description area. Until then, see you in the next video. Have a great day ahead.